So the goal of this video is to wrap up what we need to know about stoichiometry. I have here on the board a couple things to help you keep in mind of what's taking place. So when we look at stoichiometry, the actual term stoichiometry is only looking at the mole-to-mole relationships. We do not care about grams from the standpoint of doing calculations. The only thing we care about grams is that's what we can measure in our laboratory. So what you need to be aware of is that stoichiometry looks at the mole-to-mole relationships between the substances. It is only moles. So you have to be able to convert back and forth between moles and grams. So when we do an experiment, or when a chemist goes into a laboratory, or your pharmacist starts making their medications, the idea is you have to measure things out in grams to be able to put them into the proper context of how those things react. If you cannot convert between grams and moles and grams, you need to go back to those two assignments, moles to grams, grams to moles, and make sure you get 100% on that assignment, because that is an imperative that you must be able to do. So what we're going to look at today is to add one more piece to it. When we do chemical reactions, they don't always do exactly what we want to happen. For whatever reason, in real life, there is something that gets in the way, an inhibitor, some type of an interference that doesn't allow perfection within our chemical reactions. It's totally acceptable, totally fine. Everyone knows it's going to happen when we're making stuff that you don't get a perfect result. So that's where this idea of percent yield comes from. The idea is very similar to you with your academic setting. You know that when you start to prepare for an exam in whatever subject matter, you don't really expect to get 100%. You hope you get 100%, but you really don't expect to get 100%. You want to get an A. You think you know most of it pretty well. You might make a couple minor mistakes. That is what percent yield is in a real life setting. In chemistry, percent yield is what percent of what I should have been able to make did I actually get. My mom had a recipe when I was a kid making these really awesome, amazing chocolate chip cookies. They're called orange chocolate chippers, and they're delicious, but that's beside the point. Here's what happens. The instructions say to use this much flour, this much sugar, this much cream cheese, chocolate chips, all the stuff that you add into it, and it says you should yield 36 tea-sized cookies. That's those really itty-bitty, tiny little, they're like 1-bite cookies. They're awesome. Well, every time we went to make them, we probably made them a little bit too large. So instead of getting 36 cookies on a cookie sheet, we would get like 30. So what was our percent yield? Well, we would take the 30, what we actually got, the actual, divided by the theoretical. The theoretical amount was the recipe said 36 cookies. And I would end up with a percent that is less than we should have been able to get. Somewhere around 80% in that case. All right. So now, when we start to look at this in a real chemistry setting, what ends up happening is these add a whole nother layer of difficulty, because they're going to give you different pieces that you have to put together. They're going to give you a stoichiometry problem. The one that we're going to do together, I actually give you the balanced chemical equation ahead of time. If you have the balanced equation, then all you have to do is solve the stoichiometry and then figure out that's the theoretical amount. What's my percent yield based on what I should have been able to make? So let's look at this problem together. So I've covered up the numbers so you can see this. The balanced equation says that 2 sodium peroxides react with 2 waters to form 4 sodium hydroxides and 1 oxygen gas. So if a chemist does this reaction and they take 10 grams of sodium peroxide, so we're going to start with 10 grams of this stuff, and we react it with excess water. So that starts to bring in the idea of limiting reactants. I have excess water, which means it's never going to run out. The sodium peroxide is the limiting reactant. It will get used up, and that's all we really care about. How much sodium peroxide reacts controls how much product we're going to make. So if she reacts this much stuff, and at the end, they give us some information like, okay, what's this? They actually collected, this chemist collects 1.77 grams of oxygen. What is her percent yield? So what you're going to see is we're starting with 10 grams. This is the heart of the problem. That's why I wrote this little heart. That is the heart of the problem. That is the stoichiometry part of this reaction. So if we started with 10 grams, the first thing we have to be able to do is convert grams to moles. I don't care about grams. That's what we measure, but I can't do anything mathematically with it. So I need to convert from grams to moles. I do that by dividing by the molar mass of sodium peroxide. If you add them up off the periodic table, there are 2 sodiums and 2 oxygens. The molar mass is 77.98 grams. This allows me to convert between grams to moles of sodium peroxide. All right, that's all we've done. Whatever this is, 10 divided by 77.98, that number's in my calculator. I don't really care. We're going to leave it, and we're going to keep going from there. That's how many moles of sodium peroxide we're starting with. The next thing that we're going to do is the stoichiometry. This is the hard part, but it's not. We're going to look at the balanced chemical equation and say for every 2 of these sodium peroxides that we begin with, we can make 1 oxygen. That's what we care about, because it says when she does this reaction, she collects 1.77 grams of oxygen. So I want to know, how much should she have been able to collect? So for every 2 peroxides, molecules, moles, whatever, for every 2 moles of this, we will get 1 mole of oxygen gas. So that mole to mole ratio is a 1 mole of oxygen on the top, 2 moles of sodium peroxide on the bottom. This allows us to move from here, let's get the pin back, from here to here. Now I know if I stopped there, this is how many moles of oxygen I produced. But notice we don't care about moles. We want to know percent yield ultimately. So I need to know how many grams this is to compare grams of oxygen. So the last step is to convert from moles of oxygen back into grams by multiplying by the molar mass of 32 grams. If we were to go through this mathematically, I'll take it back to blue. 10 grams of sodium peroxide, grams of sodium peroxide is on the bottom here. Okay, it's green. Grams of sodium peroxide cancels. Moles of sodium peroxide to moles of sodium peroxide, those cancel. Moles of oxygen, those cancel. And I'm left with grams of oxygen as the only thing that went off my screen. Sorry, you can't see it. 10 divided by 77.98 divided by 2 times 32. When I do that, my theoretical yield, whenever we do a problem on paper, this is a theoretical answer. That value, when you push this on your calculator, you should get 2.05 grams. That's how much this chemist should have produced if this was a perfect reaction. But they told us that when she did this, she only collected 1.77 grams. In order to find the percent yield, we want to know, what is her grade? What did she get? What percentage does she have? So we take the 1.77 grams divided by the 2.05 grams that she should get. This is going to give me a decimal, so I multiply that by 100 to find our percent yield. Again, this is the percent yield, not the number of grams of oxygen produced. It's the percent. So 1.77 divided by 2.05 times 100 is 86.3%. So a lot of people would say, oh, wow, well, what'd she do? What'd she mess up on? Nothing. She did the experiment. It reacted. For whatever reason, some of it didn't completely react. And there was 86.3% of what she expected was actually produced. All right? These percent yield problems ask you to do stoichiometry and then compare what you theoretically should get when you do the real stoichiometry with what happens in the laboratory. So when you do an experiment in a classroom, you mix things together. You should have produced 2.5 grams, in this case 2.05 grams, and when you measure it out, you're like, oh, well, you didn't get that. That's not what we got. What did we do wrong? And that's okay. You know that you're expected to get a little bit less. In real life industry, chemistry people, whatever you want to call them, again, those pharmacists, those industrial chemical engineers, they have to decide, is this going to be productive enough for our company? Typically, if you get above 50 to 60% of your percent yield, that's going to be acceptable. They're like, all right, let's go with it. Unless it's a super duper expensive process, then they have to do all kinds of other risk analysis and financial constraints, all kinds of things that in our class, in a chemistry setting, we don't really care. We just mix the stuff together. What did we come up with, right? So in order to review all the stuff that we've talked about in this unit so far, it's pretty simple. There's been 5 things. We called it simple stoichiometry. That's using the mole-to-mole ratio. That's what I just said is the heart of the problem. We also did 2-step stoichiometry. In those, there's going to be at least one, no, not at least, there will be one conversion between moles and grams. Either they will give you grams and ask you to solve for moles, or they will give you moles and ask you to solve for grams of something else. Three-step stoichiometry, this is the key. This is typical, like everyone should be able to do three-step stoichiometry. That's where they give you grams of one substance and you're solving for grams of something else in that chemical reaction. The fourth thing that we talked about was adding one more layer to it, is the idea of limiting reactants. What is going to be used up? What gets consumed? What is gone? And I can't keep making more product. So with limiting reactants, they will tend to give you two values of reactants. They will say, if I reacted 10 grams of A with 10 grams of B, how much of C can we make? And it's not 20 grams. It's some other chemical reaction of what's taking place. There's a limiting reaction that's going to occur. And then finally, what we just covered right now, this idea of percent yield. What percent of my target did I actually produce? As we go through all of these things, you are probably aware by now that there are a lot of chemistry assignments on Moodle that you should be completing.